Welcome back to the next video in the series. We are continuing with the 4 wave behaviors, and now we're going to be discussing refraction. Refraction is when a wave travels from one medium to a second medium. The original wave is redirected at a different angle, and it bends from the normal surface. The frequency remains the same, but the speed and the wavelength change. So we're going to look at this for water waves and eventually for light waves, but today's lesson will focus primarily on water waves, as you see in the first diagram. Light waves are identical, but the drawing is slightly different. So we're going to look at a simulation that explains wavefronts approaching a boundary and then crossing over. Let's take a look at a sample problem first. Now, I've chosen this problem because there's a wonderful teaching diagram from one of the physics regions. The refraction summarized. The diagram below represents a straight wave front passing from deep water into shallow water with a change in speed and direction. We're going to explain this diagram in tremendous detail. They want to know what phenomenon is illustrated in the diagram. Well, the answer is simply refraction, but we're going to have to explain all of that starting right now. So, this black line represents a boundary. And in the case of water waves, this side of the boundary is shallow and this side is deep. So we're going to look today at how the behavior of this wave changes at the boundary. So the difference in distance between each one of these lines in the deeper water, that is called the wavelength. The wavelength. It is a longer wavelength. When the wave hits the boundary, 2 things happen. First, the wave changes direction, and second, the wave slows down. So we have 2 observable behaviors. The wavelength decreases, and of course, the velocity compensates and decreases as well. Now, this is a static picture, and it doesn't really help us very well. But when we go over to the simulation, we're going to see this in action. So let's make sure we understand what the parts are. So when we get there, you'll be able to transfer and apply what you see here. This blue line is the ray that represents the movement of all of these wave fronts. The distance between wave crest to wave crest is a wavelength. This orange line represents the 90-degree mark, or the normal line, off of this surface. When the wave meets the surface, the ray of this wave makes an angle, theta 1, with the normal. If there was no boundary, the ray would just love to continue along this blue dotted line. But because the boundary is in the way and it redirects, it bends the wave. The word refraction has the word fracture in it, and a fracture is like a broken arm. The bone is bent. So the ray is bent and it follows this green path. It now makes a refracted angle to the other side of this normal, right here. That's theta 2. So it comes in at theta 1 and it crosses the boundary and bends to a new angle, theta 2, which is less than theta 1, especially when you're going from deep to shallow water. All right, let's take a look at a simulation, and we're going to come back to this problem and see it again. Here we're at the simulation, and we're going to watch a wave refract across a boundary. A wave will start in this zone here, and then it will cross this yellow boundary here, and it will go into this side here. Let's take a look at what that looks like when I start the simulation. So I've just created waves that are going to come through this material and meet this boundary, and you can see right here they just started to cross. We're going to take a look at what happens step by step. That's enough to look at. I think it's going to really bring the point out. All of these waves here maintained parallel crests, but if you notice, the line is bent. At the yellow boundary, every one of these waves is bent back. That's because this material and this material, or this medium and this medium, cause the waves to travel at a different speed. The fact that these are lagging behind, you could tell this material down here causes the waves to move more slowly. And in doing so, the wave length between black stripes, which represent the crest, have smaller wavelengths than they did before they cross the boundary. Let's let this wave train pass by and see what happens. All right, now these are partially reflected waves over here. Here's a new fresh one coming in. Now notice the spacing changes. The wavelengths decrease. It also gets slower. One more time. All right, very good. I'd like to point out right now, this yellow bar represents the source of the waves, and I'm going to turn on the simulation and we're going to study the direction that the wave train follows. So here it goes. You could see that it passed straight through and then turned when it got to the boundary. I'm now going to turn the yellow bar to make it parallel to the boundary so that the waves come out and they hit the boundary at 90 degrees. Let's take a look at what that's going to look like. I'm going to start the simulation. I'm going to watch the wave flow and travel from its source towards this boundary. We're going to observe something very unique about this wave. Right now I have it set so that when the wave starts, the wave crests will be parallel to the boundary. Let's take a look at that. And there they are. All of these wave crests are parallel to this boundary. So what behavior do we expect to see when the wave crosses the boundary? Well, let's take a look. Notice that there was no bending in this wave. That's because this source is parallel to the boundary. The ray, which represents the direction and speed of the initial wave train, comes in along the normal, and therefore, since it has a 0-degree angle of incidence, it will also have a 0-degree angle of refraction. The only difference you can see here is that the refracted waves have a smaller wavelength, which means that they've slowed down on this side of the boundary. Now let's look at a different angle. In this view, I've tilted the source of the waves on a diagonal and I will set them in motion. And you can see how the wavelength is the distance between black line to black line, crest to crest, trough to trough. Once it hits the boundary, the first part of the wave to hit the boundary crosses and slows down, in a sense, dragging behind the faster moving wave. And there you go once again. These black original crests and troughs are parallel to the source. But these crests and troughs in the new material are no longer parallel. They've slowed down and bent backwards or away from the normal. It's often very difficult to see this concept explained with water waves. We can also show it with light waves. This concept can be demonstrated with this FET. This FET is actually showing a laser beam, and even though these are light waves, water waves and light waves both refract similarly when they cross a boundary. So what I want to point out here is this. On this side of the boundary, in this particular place, the wavelengths, or the distance between those stripes, is much wider than it is on the other side. This wave comes in along the normal to the boundary at 0 degrees, so it has 0-degree refraction. But it does slow down, and you can see these stripes look like they're faster than these stripes are moving. These wavelengths of these stripes are wider or longer than these wavelengths of these stripes in this material. So it looks like the top material has a faster flow of wave with wider wavelengths. And below the boundary line, you can see a tighter grouping of wave crests and a slower progression. Now I'm going to demonstrate refraction very gently by tilting this wave generator off so many degrees. And this is 20 degrees approximately that I've tilted it. What do you observe here? Some of the wave is partially reflected. So this, which is blurred out, is at the same angle as the incoming wave. So this is your incidence, This is your reflection. Just like in the last video we talked about reflection. But the majority of the wave passes through the boundary into the new material, and you can see the wave lengths in this part are wider and the wave is moving faster. On the refracted side, in the different material, you have an angle of refraction. This happens to be 13.7 degrees. The original incident was 20 degrees, so it did not just pass straight through. It actually slowed down and bent towards the normal. Now, if I tilt this a little more, you could really see it now. And here we have an incoming wave at 60 degrees to the normal, meets the boundary, and even though part of it reflects at 60 degrees, most of it refracts when it crosses the boundary and has a lower speed and a shorter wavelength. Let's take a look one last time at the diagram for the refraction, and we can see now wavelengths which are longer on one side, in this case the deep water, but are shorter on the other side, which is the shallow water. So the wave comes in from deep water very fast. V1 is fast, but V2 is slow. Since the frequency cannot change, the speed to wavelength ratio has to be the same. There are some mathematical rules that you find over here which are directly related to light waves and do not apply explicitly to water waves, although analogies could be made. We're not going to get into the letter N at this present moment, but we will just talk about this relationship of speeds to wavelengths. And here it is. This is very important. The speed in the first material compared to the speed in the second material is equal to the wavelength in the first material in proportion to the wavelength in the second material. That's really the main point that we want to drive home today with water waves. When we get to refraction of light, we will revisit the same diagram. We'll change the PhET from waves to a ray, and we'll discuss that on another lesson. So now we will conclude this video on refraction and summarize briefly. When you're dealing with water waves, from deep to shallow, fast to slow, long wavelength to short wavelength, the angle of incidence is related to the angle of refraction by a formula that has to do with the sign of the angle, but we will not have to deal with this formula until we deal with light rays. Thank you for watching, and we'll see you in the next video.